I guess we can start a 2 minutes early, I guess. Nobody will come, or if they can, we can later. So, welcome to lecture. So, probability statistics lecture number 7 out of 13. So, we are already down here. We pick now 6 more and we are done with the semester. One important announcement for you and for the ones that are listening to this video, there's not going to be a personal lecture next week, so you can sleep a little longer. I will post a recording that for personal reason I cannot come next Tuesday, and we meet again the week after for I think it's the last lecture before the Christmas break. Okay? So don't come because you're going to be very frustrated, and I don't want your anger against me. Today is joint distribution, quantiles, moment generating function, and method of moment estimation of parameters from the distribution. So we have quite to cover. Let's see how we do it. So joint distribution is something that we already have seen, but we define it here within the continuous domain. Then we describe quantiles that you probably have seen before, so it's the median, the lower and upper quantiles, and we define what a box plot is, which is a very important or useful tool. Then we say we go through moment generating functions and how we can create moments or define moments from a distribution, and then how we can estimate parameters of a distribution with this concept. Let's see. So joint distribution, and I guess I'm moving this guy also always one here. So joint distribution or bivariate distribution is a distribution that is valued not only in one variable but in two, and it pretty much have the same properties as the univariate distribution, but now you will have two random values that can take. And an example of this could be, for example, what is the probability if you are 1.7 meters tall to be 200 kilograms weight? Okay, so usually they are in some way joined, right? Because how tall you are is related to how much mass you have and how much weight you could have. Usually, you could think about that. So I define it for x and y, for example, in this case, and that it can take any value between a small x and a small y. Don't worry about the border set. It's just that x and y have to belong to the 2D spectrum reality. Okay. So how we define the probability, the joint distribution is by, again, integrating, as we always do. Now it's a double integration because we have to integrate over x and over y. And depending on what you want to get, in which direction is where you're going to integrate, in which direction you will integrate in the other direction. All right? So sometimes this probability function or joint distribution f is called h in the literature, so we use h, but it's just a name or a letter here that changed. And then so the probability of x to be that belong between a and b, so two limits, joined with the probability of y to be between c and d is the integral of this h in a and b, and then in c and d, and then a and b. Okay? And basically what you're doing is, depending where you're integrating, if this is your probability density function, for example, now you can see it's a 2D function, and then you would maybe integrate in one direction, or you integrate in the other direction, and then you will get your probability function as we saw before. Okay, and that is all. There is nothing else. All the properties that we have seen applies to bivariate joint distribution. And these marginals of this function can be useful. So for example, you will have the continuous uniform joint distribution, right? Where the probability function or the density function of H is 1 over some constant value V, the absolute value, right? No matter where you are in X and Y, that's what they say here. And then you could have also the two-dimensional by the joint standard normal distribution, right? And this is what also that I showed in the previous slide. And now the difference is that you have X and Y in the exponent of the exponential. So nothing really, it is also, you can see that it's the sum of them. This is interesting because this will help us define later how you calculate the spread of this distribution. Because now, before we have it, the distribution, then how much the spread around the mean was the variance, right? Now you have a 2D dimension, so how you actually see this spread over a plane, not over the line. And that's what we're going to define in a few minutes. So this will be the cumulative density function of the bivalent distribution. Remember that the other one was just like that from tables. Now you have a 2D version of that. And this is what I was saying. So now, if you take, first you can actually calculate the marginal distribution, which will be the univariate in each direction. So if you integrate the function x over y, you will get the marginal of x. So you're going to get this part, the blue one. And if you integrate over x, you will get the y section, right? That's what you're seeing here. And in the middle here you have the joint distribution, right? And you can see that the points now are spread, like I say, in a plane. They're not spread in a line, right? And one thing that changed is that now it was, before was the variance was something that we say, okay, this thick portion is the defining kind of the variability. Now you have an area, and this area has some kind of orientation. Okay, so you can see that, right? Could be more oriented towards one of the variables or to the other, and it's also spread, or wider or thinner. And there's a way to quantify this, and we'll see this, how we do that. Yeah, that's important. So you can have bivariate joint distribution of any function, like for example, this is sometimes called Mexican hat. This will be a 2D sinusoidal function with some linear side on the other side. This is whatever, and you can even have the discrete version of the joint distribution, which is something that we already kind of saw, right? So, like I said, it's the same thing, but in 2D instead to be in 1D. So, for example, here we can have one example. As always, let's say that we have a joint distribution or a bivariate, a random vector x that is x and y, right? And it's uniformly distributed, right? And it's such that it's like we see here in this figure. So x goes from 0 to 1 and y goes to 0 to 1, and it's related by this line here, this IR, okay? And the density function, the joint density function here, h, is just 1 over a, okay? And a is divided half of this square that is formed by these two variables, okay? So it's basically 0.5, so the joint density function is just a constant 2 because it's a uniform distribution, okay? So how we can calculate the marginals f of x in g of y? And then you have to integrate this h over dy if you want to get f of x, and you have to integrate h over dx if you want to get g of y, okay? And then if you have integrated, of course, between a and b and c and d, as we saw before. So in this case, it's 0, 1. And So we can take, of course, the 2 outside of the integration, then we have just a constant. The constant will be just x, right? And then you can evaluate between x and y, x and 1, and x, of course, can take only minimum of 0, okay? So if you evaluate between x and y, you will have 2 times x and 2, right? So it's just that, because this is x. If you do, then you will have this. Move this guy here a little bit. Then you will have, this is our f of y. So it's just go from 0 to 1, and you start with 2 when this guy is 0. And then it starts to reduce, decrease until you get to 0 when this guy is 1. Okay? And if you repeat the integration over dx, then you will get 2 times y, and this is the plot of that, the graph of that. Okay, so nothing really crazy here. I keep saying that nothing is crazy here in this lecture, nothing is crazy, so, but I hope this is just straightforward for you. So, joint distribution then is how 2 variables, how 2 probability functions move along together, right? And as always, it can be related or it can be unrelated or stochastically independent, as we saw some times ago, right? And if they are stochastically independent, they don't share any information, then basically the joint distribution can be just the multiplication of the probability function of each of the variables independent, okay? And this is useful because you will see later how we can use that. So basically, the h can be defined by just multiplying the 2 marginal functions separately and then calculate them separately and then multiply them together, right? So this is important. So, but like I say, we saw that now it's a 2D structure, and we have a 2D variance, right? It's a spread of the points are actually in a plane, and this variance can have some kind of a direction, right? And then how we can actually calculate that? Well, we calculate with this they call covariance of the distribution, and this will lead later to what is the correlation coefficient, famous Pearson correlation coefficient or correlation coefficient that we'll discuss later. So, but what is the covariance? So we are talking about 2 variables, right? And we want to know the variance of the sum of them. Okay, so what will be the variance of that is given by the one of the marginal plus the variance of the other marginal, right? And if you sum it together, it will give you the variance in total of the joint distribution, right? So if you do that and remember how variance was calculated, we just take the variable that we want to calculate the variance. In this case, it's the sum of x and y, right? And we calculate the expected value of this sum minus the expected value of the sum. Everything is squared. Okay, that was the formula for calculating the variance. If you do that, here, to make it easier, when I say E of x or E of y, I just say the expected value of x and the expected value of y, okay? Because if not, it makes it like a really long thing. And then, so you can actually expand this by just calculating the expected value inside of the bracket. And then since you have a square here, if you remember when you have a, I think it's called binomial equation, then you can expand it as the square of the first term plus the square of the second term plus 2 times the 2 times together multiplier, right? And this is what I do here, right? And if you do that, then you can start noticing 2 elements here. It's basically the variance of x and the variance of y. So basically the variance of x plus y is equal to the variance of x plus the variance of y plus some term here. There is a new addition that we have. And this is, if you take out the 2 here, is the covariance. Okay, so you will have the total variance of the joint distribution will be given by the variance in one direction, the variance in the other direction, plus the covariance, so what they share as a variance, okay? And this is basically what you see here. This is spreading, okay? The less they share, this spread becomes more thinner, okay? The more they share, the more the covariance is, the bigger it might be the circle, okay? And this is basically it. It's defined here. Sometimes it's called covariance, okay? You can see it like that. So you just forget about the 2, and then you get your covariance. Like I say, another way of defining the covariance is you could take a function now that is defined like this, right? And then if you integrate, if you calculate the expected value of this function here, covariance, instead of the probability density function that you will have, then you can get the expected value of this function, and then the expected value of this function will be nothing but just the covariance. But this is another way of obtaining the covariance, which I found that the first one much more intuitive and easy to relate to. So once we have defined the variability between these two functions, right, that are joined together in a joint variable density function, then you can define the coefficient, the correlation coefficient. The correlation coefficient is what given by Pearson. Pearson, you know Pearson correlation coefficient. It's basically taking this covariance and divide it or normalize it by the multiplication of the standard deviation of each variable independent. Okay, that's it. There's nothing so difficult on the correlation coefficient. And what you're doing basically is making, if you think about that, you're making a ratio of what they share divided what they actually given to as a variance to the distribution. Okay? And then this ratio, the larger this ratio is, the more correlating they are, the more related the signals are. What that means that they are correlated related is that when one is larger, the other is larger too, or when the one is larger, the other is when the other is smaller, the other is smaller. So it's like they work together. Okay, they go together. Okay. What you say when they are not related is when one variable is changing and the other doesn't at all. Right? So there are no correlation between them. And it basically is that ratio, because what they share over what they independently provide to the distribution. And given the Cauchy-Schwarz inequality, which I'm not discussing here, you can always say that the ratio, so the numerator will be smaller than the denominator, so it can always be at least at a maximum 1, and it's going to be less than 1, okay? So it can be 1 or less than 1. And since the covariance can go in one direction or the other, so every time I talk that. So since this circle, this ellipse here can move in one direction or the other, right, depending on how they share the variance, this guy can go between -1 and 1, okay? So this was -1 here. All right, so that is what you see usually, correlation coefficient in -1 and 1. And these are examples, for example. So these are a few points that are distributed in different ways. So you can see that if they perfectly align, so there is not a spread, that they always follow a linear relationship between the one variable, let's say that this is y and this is x, then you will have a perfect one correlation. In this case, since when one is increasing, the other is decreasing, you have a negative correlation, so -1. In the second graph, you have a positive correlation, so you have perfect positive correlation of 1, because when one increases, the other increases. And here, you will have not a perfect correlation, so it has to be not 1, so it has to be, it is negative in some way, so it's always going to be below 0, but you can see that there is some difference to fit in a line within this relationship. And this is the spread, this is where the covariance, if you want to start to play more. And then you will get something like this between 0 and -1. And the same thing here, okay? And the last one is, if you are looking for correlation, is the worst case, because basically here you could fit any line and you will get always the same result. So it's a zero correlation, okay? Because there is no way to fit a line that is unique to this point, okay? So you have a correlation of 0. So these are examples with more points. This will be correlation coefficient here. And you can see again, the more the cloud gets more spread, the less correlation that you have. And this is, and of course, the more data that you have, the more points that you have, usually you can see the real true distribution of the point, all right? So these are all 0. You can see it because one line you can cross here, right? So there is nothing that you can actually find a relationship between them. So the covariance can be also distributed in different ways. So it can be, for example, this is how the points spread for different functions, right? And here the covariance have been uniformly distributed. So you can see that for all the points, you have pretty much the same spread, okay? You can have also normally distributed, that the points are more concentrated in the middle. You can see that in this heat map here. And you can also have, for example, other kind of bimodal, distribution, and then you will see that the points are spread more on the one and the side. So what this makes to you is depending on your problem. Sometimes you like to have an uniform distribution of your points. Sometimes you want to have something like that. This might be, for example, something to cluster things, right? And then you can look at the covariance of a joint distribution to find information in one part of the signal, information in one part of the spectrum. It can be anything. So, but the important thing is that the point can be in some way grouped with the covariance information. Okay? Because at the end, the covariance will give you more information than just in a straight line, right? So it will give you more how these two signals or two distribution connect to each other. The last thing on joint distribution is convolution. You might hear this if you are an electrical engineer or computer science, I guess, also. Is because it's used a lot in filtering and many other things. And you can think about the convolution. Usually it has been told you that it's integral of one signal times the other delay, right? And then you you pass this signal over the other, and then you get your filter, right? So this is kind of the idea that you already, I have in my mind when I remember convolution. But you can put it also as a joint distribution, which are the two signals or the two variables are independent, okay? If they are stochastically independent, then you can just find the joint density function by multiplying them, right? That's what we saw a few slides before. And then if you are talking about a variable that is the sum, again, of the two random variables, then every time x gets some k, y will get c minus k, right? And then if you calculate the expected value, that is where you actually, or the expected value or the h, is where you get the convolution of these two signals, right? So it's just one, and the marginal of one of the joint distribution times the marginal of the other part of the joint distribution integrated, and then you get your convolution of f and g. Just as a, let's call it, anecdote on this. All right. So that is for joint distribution. We go now to other descriptive. These are other descriptive parameters that we use quite a lot when you describe. You can see that we are slowly getting out of probability. we are moving now more to the distribution of the probability distribution, and then we're gonna start to go into statistics. So we are leaving the probability part of this class, and we move into statistics. And then, when you're statistically analyzing what is called descriptive statistics, one of the things that you usually like to do is to measure how the data is distributed. Basically, have some measure beside the mean and the standard deviation. You can have other methods, other parameters that are sometimes very useful when you don't have a normal distribution of your data. And these are these quantiles, okay? And different quantiles will give you different information. But mainly you can think about this. So let's say that you have your distribution here, whatever this distribution is. You can see that it doesn't have to be a normal distribution or anything standard, just any distribution. And let's say that you place some QP or P point in some part of the distribution. Then to the left of the distribution, you will have 100 times P. So if you say 0 to 100, right, of the point, so percentage of the point. And to the right, you will have 1 minus P times this 100, right? So you can slice the distribution in some point and then divide. And depending where you put this point that you divide the distribution is what the quantile, this will be your quantile, and depending where you put this quantile, they have different names. And you probably have seen this. So if you put it just in the middle of the distribution, it will be your median, that's called, right? If you, let's say that let's graphically do this. Let's say that you have something like this. This is your distribution. This is probability, and this is your value of x. Then, I don't know, the median will be something like here, right? So if you take the median and you go to the left of the distribution to the lower part, and again take this middle part and divide it by 2, then you will have the lower quantile, the 25% of your data there. If you go to the upper portion and you divide it by 2, you have your third quartile, the 75% of your data. And that's what actually see here. So it would be something like, I don't know, maybe here and maybe here. So this would be your median, your first quartile, and your third quartile. And sometimes the median is called the quartile number 2. And then the difference between the upper quartile and the lower quartile is called the interquartile range. Okay? So if you have something like that, then, and the median is in some way also defined because you have to cut it in half, depending if you have uneven or even numbers. It could be just the middle of the distribution, or it can be the average between two values, right? Because you cannot really equally divide it in 2. So if you have something like that, and this is maybe nothing new for you, you could, instead of having all the distribution and all the thing there, you could just draw a line for the median. You can draw a line for the upper quartile, a line for the lower quartile, and you can join it together and make a box. Okay? And then sometimes you like to know what is your maximum value and your minimum value that you can get in distribution. And this is what is called a box plot. Okay? This is a box plot. Nothing else. And then you can have this nice plot that basically synthesizes or summarizes your data. Okay? And this is a really nice plot. I think it's much better than bar plot or other plots that are actually hiding. It's not like hiding information, but this is very explicit. You can really see here how much variability you have in data, where are the maximum and the minimum, where is the middle or the center of the distribution, right? Then if you have something like this, for example, then you have other distribution, and then maybe you have the median here, the lower quartile, the upper quartile, it will be in the other direction. Yeah, something like that, P and X. Then you can have median, upper, lower, maybe something like that. Then you can see if two distributions are different, for example. Because if the medians are different and the variance is not so large, then you could see usually a rule of thumb is the lower quartile does not touch the median. Usually you can say that they are different. Okay, you will see that there are methods to statistically prove if two distributions are different. Okay, we'll see that later. But that's what a box plot is, and usually what a box plot looks like. Some people like to also plot the points, right? And you can also define outliers, which are points that actually are too apart from this box plot, and you can see, maybe this is not real data, maybe it was a failure of the measurement or something. Then one typical rule of thumb is to say, if it's 2.5 times the interquartile range, if the point is so apart from the box plot, then maybe it's an outlier. But this is something that it can be a science itself, to how to define outlier, how to remove outlier, and when you should remove it and when it's not. This is something else that we can talk in another day. So, all right, so joint distribution, covariance, Pearson correlation coefficient or correlation coefficient, and quantiles defines our distribution, right? So let's go into one topic that is important to describe or also to synthesize distributions, okay? So what is the moment generated function, or in this case, this particular is the common moment function. So let's put it like this. There is a function that you can use to generate distributions function, okay? There is actually a general way of, depending on how you play with the parameters, you can generate any function, which is pretty cool, right? And this will depend on the moment of the distribution, okay? And we have talked about moments, but we didn't call it moments, okay? So one moment, for example, is the mean. Another moment is the standard deviation or the variance. Another moment would be, like we see, the skewness or the kurtosis. And this moment defines the shape, the morphology of the distribution. So if we can combine this moment together, we can create any distribution that we want. Not like that, but the more basic distribution that we have, okay? And there is, these are what usually we call it characteristic parameters, so the mean, the standard deviation, and so on. So let's say that we have a function. Don't ask me how this was found, but this is what is called the function that defines the common moments. The common moments are the one that I talked to you. So mean, standard, mean, variance, kurtosis, skewness, and so forth. Okay. Because there are other moments that we didn't even, I don't know, maybe I even never saw it. So, but this function is just the effective value of the variable x, the random variable x, minus some r, parameter r, and everything is to some parameter k. And depending how what r and k takes, it will define your moment. Okay? That's it. So, for example, you could already imagine how the variance is defined and how it looks r and k when you define the variance, okay? But we're going to go through this easily now. So let's say that we define r here as mu, as the expected value of the variable x, or mean that we call it, right? And let's keep k as just an integer that it can go from 0 to 2 to 3 to 4 to any value, okay? So if we do that, we replace r by mu, and we change k, then we will have the central moments. These are called the central moments, okay? Because they are centered on the central part of the distribution, which is the average, okay, the mean. And it will change over k. So this will be the formula for the central moment. We are just replacing r by mu, and we leave k as it is, right? So the expected value will be, as always, the sum of the variable times the probability of this variable to happen. Okay? So let's say that k is 0. If k is 0, what happened? This is 0, right? And the moment of 0 will be just the moment of mu, which is 1. Okay? If k is 1, then this guy becomes 1, right? And then we only have the expected value of the difference between them. And if you remember that the law of the large number, this difference, as we go to infinite, tends to be equal to 0, or that the expected value of x tends to be mu. Okay? So that's basically what it's saying here. The moment number 1, the central moment number 1, if you want to call it, is mu. Okay? If k is equal to 2, then now we have k2, now we have a 2 here, and this is something that you already can see it's the variance, right? If k is equal to 3, then we have a cubic here, and this is very similar to the variance, but it's called the skewness. And the skewness of the distribution is how, so for example, this will be a very, with a low skewness, this will be a high skewed distribution, and this will be more like, sorry, these drawings are really bad, sorry. Skew to the left, skew to the right, okay? And how much the distribution is skewed will give you a larger skewness if you are more skewness, and the sign of the skewness will give you if you go to the left or to the right, okay? And we can have now a sign because we have a cubic here, and then this can actually have a sign, negative or positive, okay? And the last one that I just touched here as a common or central moment is when you have k equal to 4, and this is what's called the kurtosis, okay? Kurtosis, and the kurtosis defines how steep or flat the distribution is, okay? And in this case, it's always a positive value, right? So, first moment, mu, second moment, variance, third moment, skewness, fourth moment, kurtosis. Alright, what happens if instead of having mu here, a r, we replace it by 0. Then we get the moment at null. So the before were the central moment, now we have the moment at null, that is called. And basically you can again, so you will have only x, and it will be to the power of k. And now again you can play with k. But we have only, here we play with just 2. So k equal to 1 and k equal to 2. With k equal to 1, again you get mu. With k equal to 2, you get this nice relationship, and we will use it later. It's useful for some derivation later. So the moment at null, number 2, is equal to the variance times the mean square. Right? So we have then central moment or the common moment, moments at null. Then how we can actually use that, or how we can actually generalize in a standard moment generation function. So, because in some way we want to have a function that actually generates all the moments that we actually want to have, right? And this would be useful because then if we have a function that generates the moments, then we can actually generate a function. We can generate a probability distribution by just modifying the moments. And also we could use this to find the moments of any distribution, okay, and characterize it. So there are two things. You can analyze the distribution or you can synthesize the distribution, okay? So the way that we do it is, again, we start with the expected value of some function g of x. We say that the expected value of x is this, we can treat it the same as it's a function of x. We saw that before. And let's say that this particular function is exponential to the dx. Okay. Who developed the moment generating function came up with this is where the genius comes, and I am not one of those. So you can just replace exponential of t to the x as our gx, and then you will have the effective value of this particular function, okay? And if you remember, the exponential of x can be approximated, or if you have infinite number of terms, it is equal to the power series like the one that I'm showing here. That's kind of called, I think, the Taylor power series, right? Which is x, this is summatory of x to the n divided by n factorial, okay? So you could replace now e of tx by this approximation, or if you go to the infinite, exactly that value, right? And then that's what we do here. We multiply x by t, because our function has t in the exponent, right? And then you get this nice power series that define all the moments of the distribution. And if you see that, and if you start to get then the expected value, right, of this would be our g of x, remember, times f of x. This is expected value. Then you can replace it by the power series, and then the first term of the series is 1, the second is tx, the third one is t squared over 2 factorial times t squared, and so on and so forth. And then you can see that x becomes each moment of the distribution, and the summation of all of them define the standard generating moment. And then where you cut this is what will be your approximation to the distribution. Okay? You can think about it this as the Fourier transform. Remember that the Fourier transform is you can generate any function by the summation and subtraction of cosines and sine with some weighted distribution, right? The weighted summation. And then, for example, for a square signal, you will have infinite number of cosine and sine with some coefficients that are weighted the sum. Well, this is the same. You could have a weighted sum of different moments, and then you can generate any distribution that you want. Well, again, sorry. You can define a listed distribution that we know. Okay? And for example, you will have for different, for example, for the Bernoulli, the moment the generating function of the moment generating function of the Bernoulli is this one. You see that it depends on p, right? And depending on p, you will get your distribution. Depending on different p, you will get your distribution. It gets a little more complicated for the beta distribution. I think we touched the Erlang. The exponential distribution depends on lambda, and so on and so forth. So with these parameters and the function, the generating function, you can create any probability distribution, which is, I think, really nice. The other way around, you could also estimate the parameter p, lambda, and so forth. You will see how we can use that. All right. So, this generates, and this is where it gets a little more confusing or more complex. There are many of these generating functions. Okay, and different moment generating functions have different names, like the characteristic function, the probability generating function, and the cumulative generating function. So there are many of those that we're not going to cover here, but for you to know that they will have different ones. And then the particular one, the characteristic function, could be that it was that we defined it before, right? It could also be it is also valuable in the complex domain. So when you have a complex, because the probability distribution at the end is a function, right, valued on a random variable. And this variable can be complex. And if the variable is complex, then the probability distribution is complex too. Right? You have a real and imaginary part. So all what I say is actually identical to, or it is valid for the complex domain too. The only difference is now you will have your J, right? Your I, sorry, in the because if you remember, you have your imaginary and your real part of the value, right? And then you can define a vector. So depending where this vector is in the imaginary plane, right? In the imaginary real plane, you have some angle here, and that can be modeled, or it can be described by x of the exponential function, right? Remember, this comes also from the Fourier transform and so on and so forth. So I don't go in detail this, but basically you can end up with the same moment, weighted sum of the moment, but now having to take into account imaginary part as well. And this also take into account that if you multiply 2 i's, you get -1, and so on and so forth. Okay? And don't worry about this when you just know that probability distribution that I never saw it before, it can also be on the complex domain. Okay? Alright, so, and maybe this is the breaking point of this lecture. I don't want to make it so spectacular, but this is actually when we start really to start digging into statistics and leaving the probability part. Well, we start to estimate things, right? So far we have calculated things like probability of this to happen, the probability distribution. Now, statistics is more about trying to describe some event, but when you describe it, even when you're describing it, you're estimating what will happen, because you never get all the information that you will need. You always draw a sample from a population, right? If you want to know, the distribution of the risk of having cancer in young adults, you will need to have the information from, I don't know, some biomarkers for many people, or all the people in the world that are living now and were living since the starting of the days, okay? And then it's impossible to get data from all of them. Then what you do is you take a sample from your country, you measure maybe 100, and you estimate the distributions, right? You estimate what is the risk of this to happen. And this is what we do in statistics. We take a sample of what the population is, usually the right sample. You don't take a sample from something that you are measuring correctly, that will be another story. But let's say you take a sample, then you try to estimate the distribution of this sample, so you fit a model distributed, distribution, like it could be a normal, a binomial, a Gaussian, whatever, exponential, whatever. And then once you guess this distribution, you have to find the particular parameter of that distribution that fit your data. And then you can talk about things, okay? But the very, very first part is to see, well, you see the data, well, this looks like it's distributing this kind of function, exponential. What are the parameters of this particular exponential distribution that fit my data? And that's what we do in statistics, okay? And then once we have defined the distribution, then we can compare things. We can compare distribution, and then we can see if one portion of the data is different to other. That's all that we do in statistics. Take the data, make a probabilistic model, compare these models, and draw a conclusion out of that. Okay? That's in simple words what we do. So we start with estimation, and this is what we start to see today. What we can actually estimate, well, the parameter of distribution, and the most common thing that you actually estimate are the mu and the variance, right? Because these are basically what define a distribution. Where is it centered and how much is it spread, okay? And maybe you're interested in the kurtosis or the skewness also, but mainly these two parameters are the ones that usually you do. And there are at least two methods to estimate this parameter. One is the method of the moment, which we will see today, and the other is the method of the maximum likelihood estimation that we will see, or you will listen next week in the video, okay? But today we'll see how this moment generated function actually can be used to estimate this parameter in the method of the moment, okay? And once we have these parameters, then something we will see next week is how confident that our estimation is actually real, right? And that we need some confidence interval. So interval that will say, my mean is 5, but it could be minus plus 2. So it could be 3, it could be 7. And this interval is, you say, I am 99% confident that this mean will fluctuate between 3 and 7. Okay? And this we will see later. All right? So these are the famous or infamous confidence intervals. So how the method of moments works? Basically, we start with the best estimator that we can have. We saw that before. Remember that when you have a sample, you don't have the distribution, and this is what is happening here. And what we saw 3 weeks ago, 4 weeks ago, I don't remember, is that the best estimator is that we assume that all the values have the same probability to happen. So the best estimator at the end is the average, the arithmetic average, right? This will be the moment of some parameter theta that we want to estimate, all right? So this is how we do it. So we have to find first the moment generating function that will describe or will map this moment to the parameters that we want to find. Okay, at the end, theta is what we want to find. Theta could be mean, variance, skewness, whatever parameter you want to find, right? So we need to find this function. And we can, like I said, the best estimator to do this is just taking the average. The average powered to k. And k will define the number of moments that we have. So k equal to 1 will be the average, k equal to 2 will be another moment, the second moment, k equal to n will be the n moment. Okay? And then we can basically use this function to find the parameter theta. And I'll show you an example so it gets much more simple. Let's say that we are in Europe, so and we assume that we see our data, and we say, yeah, this has to be a gamma distributed portion of the data. So we believe that gamma is the distribution. You can already see that you have to try different distribution to really obtain a good result, right? But let's say that we assume that it's gamma, and we are happy with that. And gamma was defining the density function like this, and this was our community density function, which is called different here. And it have two parameters, alpha and beta. So those are the parameters that now that we have decided that we believe that it's gamma distributed for our data, what are the parameters particularly that fit our data, alpha and beta, okay? And then we will have to have moment 1 and moment 2, because with 2 functions and 2 unknowns, you can actually find the parameter, right? So the first will be with k equal to 1 is the mean, right? And the mean, we know from the tables and from the theory of the gamma distribution is alpha over beta. And then the second moment, a null, is when we have k equal to 2, and if we are a null, then we know that it's the variance plus the mu square. You see how this becomes now useful? So with the second moment, we know that it's the variance plus the mu square, and then we know that the variance of the gamma distribution is in this format, alpha divided by beta squared, and we know the mu again, and just square it, and now we have 2 equations, 2 unknowns, we can find alpha and beta. And this is what I do here. So we can put beta as a function of moment 1 and plug it in the equation of moment 2. And then we can get moment 2 and moment 1 related each other just by alpha. And then we can solve for alpha and we can solve for beta just by the moment of the function. Okay? And how we find this moment? We use our data. This is where we fit this moment function with data, and this is what we can do here. So With the effective value of x, we call it x bar or average, right? And we know that this is our best estimator, and we know this is the estimator of this is the variance, the definition of the estimation of the variance, right? As before. Then we can just say, remember, moment 2 is the expected value of x, or the moment at null. This is mu is 0, right? The R is 0. And then moment 2 will be this, because it's mu is variance plus mu square is equal to, and here is moment 1 square. So we just plug each other, and then we replace our estimator of mu and our estimator of variance, and x here is your data. It's the data you have in hand, right? So you plug it in, and you get your alpha. And you do the same, you plug your data in, and you get your beta, right? And that's what you will do by hand, or your software will do when you say, I want to fit a gamma distribution to this data. It will calculate something like this and will give you the nice line on that. Okay, that's all. Using it is using the method of moment. You could use the next one that we will see next week. For that, then like I say, you don't need to calculate all by hand. You have here already how to estimate different parameters for different functions. For example, so for the we already know that for the mu it's just the average. For the variance is the formula we already know. We're gonna talk about this guy here later because it should be 1 over n. But this is an unbiased estimator. We'll see later. And then for different distribution, you will have different way of finding the parameter that you want. For example, for the binomial, we're interested in p. And p, you can just define it as k over n. And right is the number of possible, the particular event that we are looking into. It's the Laplacian probability, right? Then for Poisson, mu is just the average. For the exponential distribution, lambda is over 1 over the average, and so on and so forth. There are many of these, and I'm not going to cover all of them, but you have it here. So once you print this PDF, by the way, I learned that you can print it for free here in university, so print the script because you will need it for the exam. You can bring this, and then I ask you to calculate mu and variance, you know where to look at for the different distribution. Okay, this will be your cheat sheet. Alright? So I think that is all for today. So we have seen joint distribution by bivariate distribution. Then we went to move to the covariance when you have two variables, right, 2D. Then that derives the Pearson correlation coefficient or the coefficient correlation coefficient. And then we talk about moments. We talk about quantiles, how to describe the distribution with quantiles. Then the moments of the distribution, how you can actually create distribution with a generative function. And then from that generative function, how you can actually extract the parameters if you have a given set of data. All right. So with that, we conclude. I think the part of mainly the probability part, and from next week on, we start more in the statistics. Yeah. And if you don't have any questions, which doesn't look like, hope in a good sense. I'll see you then in 2 weeks. Thank you.